Thank you for the introduction, Michele. Yeah, I am Vijay. I'm here to talk about information scrambling. I'll qualify what is scrambling in a while, but before I do that, I want to clarify that the information I'm talking about here is not from the perspective of computer science. So I'm not going to talk about Shannon entropy. I don't know Shannon entropy. So what I'm going to talk about is about how chaos mediates the dynamics of information and how quantum mechanics influences that. So start with the question of what exactly is chaos. A pop science answer would be that it's exponential sensitivity to initial conditions. So how does it manifest? So take a harmonic oscillator in 2 dimensions and start with a swarm of initial conditions near the minima. And you see that with time, the system retains memory of its initial condition. There is only certain disturbance in the initial conditions you see, and it's orderly motion after that. Now, if I turn on a nonlinear coupling and squeeze it on 4 sides like that, you see that with time, the initial conditions, like the memory is lost in the system, and there is no memory of the initial conditions. That is, the dynamical information that is stored in the initial condition is lost irretrievably with time. Okay. So your initial conditions are a measure zero set in the available energy space. Yeah. So what would be the quantum analog of that? Okay. So in quantum mechanics, you know that you can't work with x's and p's, that is position and momenta. You have to work with operators. And in quantum mechanics, you think of one way to think of quantum chaos would be along the lines of how operators spread with time. Okay. So how do we do that? We do that with these cute-looking functions called the out-of-time ordered correlators. They are called out-of-time ordered because you hop from 0 to t, then back to 0, and then to t again. So that's why they are called out-of-time ordered correlators. They look a bit weird. So let's try to do it one step at a time. So if you choose your W and Z to be Hermitian operators, which commute at time t equals 0, then C of t, the out-of-time order correlator, will be roughly 0 until a certain time, which I'm going to call dissipation time. That's the term used in literature. Okay. And for those who are familiar with the effects of quantum coherence, this is the time in which the time ordering does not matter in the 2-point correlation function. So that's how they differ. So that's how they do not differ from 2-point correlation functions. Now, what happens after that? Well, for that, we go into the specifics of the operators themselves. Let's say we choose W to be Q and V to be P. That is position and momenta. Okay. So if you do that and try to evaluate the semi-classical approximation to this, you get these partial derivatives, which turn out to be what are called the elements of what are called the stability matrix or the monodromy matrix. Okay. And what they quantify how much deviation you get at time t for a small deviation in your initial conditions at time t equal to 0. That's what they quantify. And you know that the definition of chaos is exponential sensitivity to initial conditions. So you can expect them to be exponential if the underlying system is chaotic. So that means that you can expect in the quantum system in some quantum systems, you can expect some regime in which this OTOCS, out-of-time order correlator, is exponential. Okay. After the the dissipation time. Okay. So this can be used to quantify what is called the quantum butterfly effect. So the butterfly effect, which is specific to classical mechanics, it doesn't translate quite well to quantum mechanics, and you can use this out-of-time order correlator to quantify that. However, the quantum phase space has finite resolution because of the uncertainty principle. So this can't go on forever, and it happens to saturate at a certain characteristic time, which we'll call T star. Okay? And if I have to give a schematic plot of that, this is how it looks like. So your quantum OTOCS, it oscillates about 0 for some time, grows exponentially, and then saturates. However, the classical approximation will keep growing. Okay, and here are the dissipation time and the T star, which I'll call as the scrambling time. So what is scrambling? This picture here, which you see, you have some operators which grow in time and they saturate. This whole picture, it represents how information travels in system. And this picture, this idea is called scrambling. Okay, now note that in the definition of C of t, I have not mentioned the ensemble on which I'm taking the average over. Now, if you put if you specify the ensemble to be the quantum-Boltzmann ensemble, that is for quantum-Boltzmann density, you'll get what is called as a thermal OTOCS. And if it is exponential, it turns out that it can only be so big. That is, it is bounded by 2 pi by beta. This was a result. This was a conjecture put forward in 2016 by Paldesina, Shankar, and Stanford. So this was a purely mathematical proof which they gave in their 2016 paper, and we started off trying to look for a physical explanation to why the bound exists. Okay, so before I move on to the physical explanation itself, I want to start by giving a motivation for why understand information scrambling at all. The simplest answer would be that it tells you, let's say you have a system which is lattice based, and you have some perturbation at time t equal to 0, which travels with time, and that perturbation infects in more and more sites with time. And information scrambling, as quantified through OTOCS, gives a mathematical explanation a mathematical formulation for this phenomena. Okay, but that in itself is not a motivation. Okay, what would be a motivation? One motivation is that it's a fundamental question as to how quantum systems thermalize. Okay, it's crucial to understand that. So, kind of a circular thing. The conjecture I mentioned in the previous slide, that the Lyapunov exponent is bounded, if the bound is satisfied by a quantum model of black holes, and not just that, there are fermionic models which satisfy that conjecture as well. So there's something common in the physics of these systems, and understanding scrambling in such systems will be helpful to find solutions to such fundamental problems. Okay, so another thing, for instance, qubits, there is another phenomena which causes information loss. So scrambling is just information irretrievability, whereas decoherence is information loss, and you want to be able to tell apart one from the other. Okay, that is important, for instance, in quantum computing. And the other is scrambling, at least exponential scrambling, will allow for the complete exploration of the available Hilbert space of the operator, which apparently helps in the design of quantum algorithms on qubits. I have to say that I'm not an authority on any of the applications here. So if you ask me, I'll just redirect you to some standard references. I'm sorry about that. Okay, so now coming back to the physical explanation idea. So first thing if you want to have a physical explanation, you want to be able to compute it first. So we want to compute thermal OTOCS because thermal OTOCS have this bound. But it says that the bound, the idea of the bound is that there is only the information scrambling, the information irretrievability can only happen at a certain rate. So it's at least for us, it was interesting to understand why exactly that happened. Okay, so in order to understand get a physical explanation, so we want to be able to compute quantum OTOCS at finite temperature. Computing quantum anything at finite temperature is a difficult problem. So we want some kind of an approximation. Okay, so there are two sources to quantumness when you consider a thermal OTOCS. One is the ensemble, the other is the dynamics. That is, one is the statistics, the other is the dynamics. Okay, so the idea of chaos is inherently classical. So you don't want in an ideal approximation, you don't want to mess with the dynamical bits of the OTOCS. So you model dynamics using classical mechanics. However, you take care of the quantum effects in the statistics, which is the quantum-Boltzmann statistics here. Okay, and you can do that using imaginary time path integrals, which is what our group does for the most part. Okay, how do you do that? You start with the partition function. It turns out that you can write the partition function as a cyclic path integral, which in the finite difference approximation can be mapped onto what are called as the classical ring polymers. So it's a classical object. It's basically if I have to give an illustration, this is how it looks like. It's a sequence of beats connected by harmonic string. So this is a purely mathematical mapping. You map a classical particle onto a ring polymer, which is purely a mathematical thing. So but it turns out that by simulating the ring polymer, by sampling ring polymers and doing dynamics with them, you can get a lot of important quantum properties, okay, at the level of classical simulation. So that's why we were after this. So here is the math of that. So you write the partition function as a finite difference approximation, and you get the ring polymer Hamiltonian, which is the Hamiltonian of the ring polymer I was talking about. You want to compute the thermal OTOCS with that. So we choose again a specific set of operators. One thing I want to emphasize here is that the choice of operators is, although here we choose x and px, it's the dynamical information in any system can be will eventually boil down to position and momenta. There is only so much variation you can have in terms of operators. So it's not too specific to study what happens in position and momenta. Right? So if you do that, you will have a simple expression of this sort if you do the approximation. I'm not going to the derivation, but this is what you'd have. So here the partial derivative you see is the monodromy matrix element of the geometric centroid, the x coordinate of that. Okay, so this is the object which we are going to simulate. And before we do that, why do this? Okay, why go through this procedure to compute OTOCS? Well, the answer to that is that it can be implemented using a simple molecular dynamic code. You just need to augment it slightly, and you can implement it with standard molecular dynamics. Another thing is that another feature of this idea is that the ring polymer Hamiltonian can be sampled using Monte Carlo approaches. Okay, and the only difference is that you have to use a small time step to propagate the Hessian, and that's the only difference from standard molecular dynamics simulation. Okay, so we'll move on to the model now, to the system we are trying to study. So the system we are going to study is a simple two-dimensional model. It's yeah, so this is uncoupled. So you have a separable potential, you have a double well in one direction and a Morse potential in another, and I'm fixing the curvature of the double well by fixing lambda to be 2. Okay, so it's just a reference. You can choose lambda to be anything. The physics won't change. Now I'll plot. So this system is not chaotic. It's a separable problem. It's not chaotic. It's just two one-dimensional systems. So if you plot one typical trajectory of the system, you see that it doesn't diffuse too much in the configuration space. So the plot you see beneath is the record of the position and momenta along x coordinate every time it passes through that horizontal line there, y equals 0. This is what is called as the Poincare section. And you see that in the Poincare section, you get a periodic orbit. By symmetry, you will have one more periodic orbit on the other side. And there will be an H-shaped figure called the separatrix, which separates these two kinds of motion. This is the simplest picture of, well, this is not yet. So if you turn on a coupling of that sort, you're going to break that separatrix. And that is the simplest picture you can have for chaos. That is the simplest model you can have for chaotic dynamics. So how does that look like? So now you see that the orbits are no longer regular. So you see that the trajectory does funny things. And if you wait long enough, this is how it looks like. It will hop onto the other side. So information in some sense is going from one well to the other. And this is called saddle point scrambling in literature because it's the saddle point at the origin is mediating the flow of quantum information. Okay, so you see that the periodic orbits are destroyed now, and you have a very diffuse structure in phase space. Okay. Now, results. So we are simulating this system with quantum, classical, and RPMD, and we want to see how the results look like, how the OTOCS look like. Okay, but high temperature. I'll come back to what TC is. So it's a very high temperature for now. That's all I have to say for now. And the lambda equal to 2, which I said, it sets the maximal Lyapunov exponent of the system. It sets the maximal growth rate of information scrambling in some sense. And at high temperature, it's not surprising that that value is classical. The quantum mechanical, RPMD, and classical value, they are roughly on top of each other. Okay, I'm computing the slope of this OTOCS from the black line, or the highlighted black line you see over there. Now, if I reduce the temperature, before that, the TC is the value itself is just lambda by 2 pi. It's called the crossover temperature. I'll come back to what is crossing over there. So if you take your temperature to roughly around this crossover temperature, if you bring it down, you see that the quantum is no longer at 2. It goes down. RPMD also goes down. Classical is no longer exponential. If you plot the temperature dependence, the classical will always stay at lambda equals 2. I'm plotting the slope along the black line of quantum, RPMD, and classical. And the classical result will always stay at 2. There is only one possibility for classical Lyapunov exponent. And after that, because the well is too steep for classical dynamics, it stops growing exponentially, and that's why you have a dotted line there. Now, if you plot quantum on top, it will slope down gradually with temperature, with decreasing temperature. And here is the bound which I was talking about for your reference. So the quantum mechanical OTOCS obviously satisfies the bound. You plot RPMD on top, this is how it looks like. It behaves classically at high temperature, and then it slowly slopes around, to obey the bound close enough to TC. Okay. So you see that there is obviously the difference between quantum and quantum and RPMD, but that difference can be attributed to real-time coherence, which RPMD cannot capture. Now, why does this happen? What causes the RPMD to slope like that? Well, since I introduced Poincare section, you can use that to visualize what happens. I'm plotting a typical Poincare section at the barrier energy, at the saddle point energy for the classical system like that. Okay, this is how it looks like. If you plot the centroid Poincare section of a typical RPMD trajectory at a high temperature, you see that the classical and RPMD trajectories, Poincare sections, they're qualitatively similar. That's because at high temperature, the ring polymer behaves, it is compact and behaves like a classical object. Okay. Now you reduce the temperature to TC, you see that around these periodic trajectories, you have a smear distribution of phase-space. Yeah, you have a smeared phase-space distribution. Okay, so I'm focusing on that temperature, and I'm plotting a typical trajectory at that temperature in the configuration space. Okay. So it starts off as a compact object in one of the wells. When it goes to the saddle point, it's now delocalized. And when it goes to the other well, it's now compact. These trajectories are what causes the smear at about the crossover temperature. Okay, so now answering the question of what is crossing over. Turns out the answer is instantons. So these delocalization you saw in the previous plot happens around these structures here, the pink shaped structure here, which are called instantons. So instantons are ring polymers, which correspond to tunneling pathways. At low temperature, it turns out that information scrambling from one well to the other is mediated by these instantons. They are not mediated by the black saddle point there. It's not one dot. It's the ring polymer go through a delocalized structure before ending up on the other well. Okay, so what are these instantons? A definition of that would be that instantons are saddle points in the ring potential energy surface of the extended phase space of ring polymer. Okay, another way to think about it. So I mentioned the partition function can be written as a cyclic path integral. So in the path space, these instantons are a saddle point. Okay, so one way to assert that is by plotting the radius of gyration of a histogram of the radius of gyration of these ring polymers, and you at a low enough at the crossover temperature for a constant energy, which the energy will be, you can plot it for any energy, but we choose the barrier top energy, the saddle point energy, and you see that it's bimodal. Okay, so the ring polymers with the large radius of gyration, they correspond to these delocalized objects, these instantons. At the smaller ones, they correspond to compact ring polymers. Now, if I filter the Poincare section which you saw in the previous slide, this one, the one on the rightmost, okay. So if I filter that with respect to this, if I filter the histogram with respect to that, if I filter the Poincare section with respect to that, you see that the periodic trajectories, they end up in the low RG region of the histogram. And the delocalized structure, they end up in the chaotic part of the Poincare section. So this tells us that you can use this as a filter to filter off chaos. And the delocalized structure are almost exclusively coupled to the high RG end of the histogram. Okay, so that, in my view, is pretty convincing that it's instantons indeed which causes the bound. There are, of course, several other ways in which you can think about how the bound is enforced. This was the most visually pleasing, at least in our experience so far. Okay, one thing is one stability criteria for these instantons reform is that you need to have the ring polymer centroid to be unstable, and the ring polymer, the first two normal modes of the ring polymer should be stable. Only then you can have a delocalization. It turns out that you can show rigorously that the centroid Lyapunov exponents will be bounded if you assume just these two. So that is, if instantons form, the central Lyapunov exponent obeys the bound. You can show that. Okay. So in conclusion, it is indeed instantonic structure, these delocalized ring polymers, which mediate information scrambling and enforce the bound on chaos, which I was talking about. And instantons, at least in our group and in the chemical physics community, came up first in the study of reaction rates. So it means that quantum information scrambling allows a theoretical framework in the same spirit as reaction rates. That is, you have a region of phase which is unstable, another which is stable, there is a gradient, and information scrambling just rushes across this gradient. That is, information rushes across this gradient to cause scrambling. Okay. Another thing is that we use RPMD here, and we showed that it obeys the bound. It means that it's capturing the minimal, it's capturing the requisite quantum effects to enforce the bound, which means that you can use RPMD-like method to compute OTOCS possibly. So challenges. Most of these models, information scrambling has mostly been studied in systems, bosonic systems and fermionic systems, which are written in second quantized form. And one thing we want to do is to find instantons in second quantized system, in bosonic and fermionic system. And of course, we want an efficient numerical algorithm to propagate the monodromy matrix, because at the moment I'm using a very small time step. And we want to show that Matsubara dynamics, it's a word I've not used before. It's a mother theory of path integral based dynamic methods such as RPMD. And we want a rigorous proof that this Matsubara dynamic indeed satisfies the chaos bound. And we also are interested in finding systems which saturate the bound and understand their physics. Find the instantons in them and attribute the quantum features to that. We want to be able to do that. So I hope I was able to convince you that information scrambling is a topic worth studying, and that instantons are responsible for the bound on chaos I was talking about. I wish to thank my group, my supervisor in specific. He supported me through this difficult work. At least for me, it was difficult. Last, on the right-hand side, is one of the author on this paper. He is a collaborator. He was a summer student in our group. My group members have been just lovely. Thank you. And here is the promised reference, set of reference.